Today we're going to look at the Euclidean algorithm. So last time we talked about the need for being able to efficiently calculate GCDs. So if we want to know whether one number is invertible with respect to a modulus, so we claim that would be true if and only if the GCD of the two numbers was equal to 1. And also we wanted to have a method for actually calculating modular inverses. Okay, so that'll be very important for us. We want this to be efficient because we'll be working with very large integers in this course. So maybe we would want to invert one number mod a, say, 500 decimal digit number. Okay, so we need an algorithm that's going to be able to do that very quickly, and as you can imagine, just exhaustively searching for the inverse in that case, even if we know the number is invertible, is not going to be a very efficient procedure. Okay. All right, so the Euclidean algorithm is going to be our method for dealing with this. Okay, so this is a simple, efficient algorithm for calculating the GCD of two integers. And so the basic idea we can really describe in a phrase. It's simply repeated division with remainder. Okay, and so we'll go through the details of that a little bit. And I'm going to suppose, just for the sake of simplicity, that my inputs into the Euclidean algorithm are going to be two integers where a is greater than b and both are positive. Okay, the algorithm still works if you drop those constraints as long as a and b are not both 0. Okay, so the GCD would be undefined if both of your inputs were 0. But just to be able to describe this algorithm with as much simplicity as possible, I'm going to assume that we've arranged things so that both of my inputs are positive and a is greater than b. Okay. And so the idea then is I'm just going to think of this algorithm as generating a sequence of remainders. So a I'll think of as the 0th remainder, and then b I'll think of as the first remainder, and I'm also going to have this counter here, m is equal to 1. Okay, so as long as my current remainder is non-zero, that means I can divide it into the previous remainder. So that's exactly what I'm going to do. Okay, so Q will be the integer quotient when I do so. Okay, and so these these sort of L brackets here are indicating round down. Okay, so round down to the nearest integer. Okay, so QM will be the largest integer quotient that I can get when I divide the previous remainder by the current remainder. Okay, and then the next remainder then would just be previous remainder minus that quotient times current remainder. Okay, so notice that will just be the smallest positive remainder I could get when dividing previous remainder by current remainder. Okay, and then I'm just going to increment my counter. Okay. All right, and I'm going to do this until I hit a 0 remainder. Once I hit the 0 remainder, what I'm going to return is the last non-zero remainder. Okay, so notice I increment m. When I see that the current remainder is 0, I go back and I return the previous non-zero remainder. Okay. All right, so notice then that the second equation in the loop, I can rearrange this to write it as r sub m minus 1 is equal to qm times rm plus r sub m plus 1. Okay, so this is just saying do integer division with remainder. And since qm is the largest integer number of times that rm goes into r sub m minus 1, that means that this remainder is necessarily going to be, well, non-negative, but less than rm. Okay, so that's why we say this is just repeated division with remainder. Note that the algorithm will, in fact, always terminate, right, because the sequence of remainders is always getting strictly smaller, but always non-negative, so I'm going to have to hit 0 eventually. All right, so let's work out a little example of this. And so in my example, I'm going to find GCD of 1134 and 525. Okay. All right, so 1134 then is my R naught, or my A. Okay. 525 is my R1. And so what I'm going to do then is I'm going to write 1134 as a quotient. So how many times does 525 go into 1134? Looks like it goes in twice. Okay, so 2 times 525. And it looks like my remainder there would be 84. Okay. And, okay, so I haven't hit a zero remainder yet, so I increment. And so notice then that in my next iteration, right, I'm dividing, so this is, so 84 is R2. So I'm dividing, right, new remainder into current remainder. Okay, so in my next iteration, 525 is sort of playing the role that 1134 did before, and 84 is playing the role that 525 did before. So I can kind of think of this as shifting these things over. Okay, and so how many times does 84 go into 525? Looks like it goes in 6 times. Okay, and 6 times 84 is 504, looks like. So my remainder will be 21. Okay, and so R3 is 21. Okay, so still not 0. And so I'm going to do this sort of shift again. Okay, so now I'm going to divide 21 into 84. 21 goes into 84 4 times with a remainder of 0. Okay. And again, we knew we had to hit 0 eventually. We didn't know how long it could take, right? So, potentially, just sort of naively, when my remainder is 21, I could have 20 more steps if my remainder happened to just decrement by 1 each time. That can actually happen in practice, but we know that eventually it's going to terminate because those remainders always have to decrease. I'm going to have to hit 0 eventually. Okay, so, in this case, m was equal to 4 when I hit that remainder of 0. So what I'm going to return is actually R3, the last non-zero remainder. Okay, so return 21, and so 21 is going to be my GCD. Okay. All right. Okay. So why does the algorithm work? So I'm just going to kind of give a brief explanation of we just did a bunch of division with remainder. Right? How on earth do we know that what we found is actually the GCD? Okay. All right, so we can sort of run a divisibility back arguments from the bottom to the top here. Okay, so notes. Yeah, of course, 21 divides itself. 21 also divides 84, so that means it's going to divide any linear combination of 21 and 84. Okay, and so if we kind of run things up here, we see, well, 525 is a linear combination of 21 and 84. Okay, and that will always happen in the penultimate equation in the Euclidean algorithm, because you'll have your outputs, and then you'll have whatever the output divided evenly into here. Okay. So 21 also divides 525. Okay. All right, but similarly, right, now that we know that 21 divides 525 and also divides 84, we can see that 21 divides 1134. Okay, so So whatever that last remainder is, just by working backward through that system of equations, we'll see that it will divide every single remainder that we found in the process, including the original two inputs. So therefore, 21 is a divisor of both of those inputs. Okay. And again, this is kind of a small example, but it doesn't really matter how many intermediate equations we have. That will always hold. Okay. All right. And then if we suppose that we have something, we would have some divisor that divides both of the inputs, then we can run things down the chain to see that it'll have to divide 21. Okay, so C divides both 1134 and 525. Okay, well, I could rearrange this equation here and get 84 as a linear combination of those two inputs. Okay. And so C also divides 84. Okay. But now that I know C divides 84 and 525, well, 21 I can rewrite as a linear combination of those two numbers. Okay. And so that means C is also going to have to divide 21. Okay, so 21 is a common divisor of those two inputs. Anything that's a common divisor of those two inputs is also going to have to divide 21. And so therefore, 21 is actually the GCD of those two inputs. Right? And again, there's nothing special about this example. It's a very short example. So typically, you're probably going to need a lot more iterations than this to actually find the GCD. But the principle of divisibility being preserved as we move both up and down the chain of equations is going to work no matter how many equations we have there. All right. Another way to check that this actually worked is because the numbers are small enough that we can actually just do the prime factorization. Okay, so 1134 is 2 times 3 to the 4th times 7. 525 is 3 times 5 squared times 7. Okay, so if we just collect all the common prime factors of those two numbers, we see they have one factor of 3 and one factor of 7 in common. Right? Of course, in practice, we don't do GCDs by factoring numbers. Okay, so why might that be the case? Well, as far as we know, factoring is a very difficult problem. So there's no known algorithm that can efficiently factor large numbers. Okay, so numbers of this size, sure, we can factor them just by doing trial division and trying all primes until we find the prime factorization. But again, suppose you're dealing with a 500 decimal digit number, well, then you're probably not going to be able to factor that efficiently. So if you've got a couple 500 decimal digit numbers, you're going to want to use the Euclidean algorithm to find their GCD. Okay. All right, so we can find GCDs efficiently, but another issue that we talked about is we need to be able to find modular inverses when numbers are invertible. So how are we going to do that? All right, so we're going to apply something that's known as the extended Euclidean algorithm. And so this allows us to always write a number, a GCD, as a linear combination of those inputs. Okay? And again, there's a conceptually very simple way of doing this that is perhaps not the most efficient way, but something that we can write down easily in the context of that previous example. So again, let's sort of back solve this system of equations that we found. Okay, so note then that, so again, if I look at the penultimate equation on the previous slide, if I just rewrite that, I can see that 21 is equal to 525 minus 6 times 84. Okay, so that shows me how to write 21 as a linear combination of the two previous remainders. Okay, but also we know that 84 was a linear combination of its two previous remainders. Okay, so 84 was 1134 minus 2 times 525. Okay. All right, so now if I substitute this, well, I guess this, in for 84 in this equation, I get 21 is equal to 525 minus 6 times 1134 minus 2 times 525. Okay, and then if I just expand that, I'm going to get 21. So what's my coefficient on 525? It's going to be 1 plus a negative 6 times negative 2, so 13, minus 6 times 1134. Okay, so now I've got 21 in terms of those initial inputs. So I've written 21 as a linear combination of 525 and 1134. Okay, so, and again, this was kind of a simple process because we only had relatively few equations. But if you could imagine that maybe, these weren't my original two inputs and I had 1134 and something else, well, then I could write 525 as a linear combination of 1134 and that something else, and then substitute in for that 525. So there's nothing to stop us from keeping on working back through that system of equations, no matter how many equations we needed to use. Okay. All right, and then there's a more efficient way of implementing this, and you can look in your textbook. So I think it's algorithm 5.2 in your textbook, listed as the extended Euclidean algorithm for finding sort of a slicker way of implementing this. But we know that regardless of how many equations we have in that Euclidean algorithm, we can always do this method of back solving and be able to write the GCD as a linear combination of the inputs. Okay. Right, now, the most important thing for our purposes here is that in the case when the GCD of A and B is equal to 1, what are we going to get? Well, we're going to get a linear combination of those two inputs, A and B, being equal to that GCD, which is 1. So we're going to get an equation of the form ax plus by is equal to 1, where x and y are integers. And so that's going to imply that b times y is congruent to 1 mod a, right? Because, well, by is going to be 1 minus ax, okay? And then remember, the idea is when we're working mod a, we're essentially allowed to annihilate anything that's a multiple of a, okay? Okay, so that's implying this congruence here. Okay, so that means, well, since b times y then gives me 1 when I'm working mod a, that means that y is actually the inverse of b mod a. Okay. All right, so again, let's do a little example here where we can easily work out the numbers by hand. Okay, so is 10 invertible in Z mod 209? If so, let's find 10 inverse. Okay, so you may want to, again, just sort of think about that question and maybe try to work it out on your own. Okay. All right, well, let's let A be 209 and let B be 10. And so I want to apply this extended Euclidean algorithm. And the first step towards that is just doing the Euclidean algorithm. Okay, so I'm going to do 209 is 20 times 10 plus 9. Okay, I still haven't hit a zero remainder. So keep going. So 10, right, so it's these are my new remainders. So 10 is 1 times 9 plus 1. Okay, well, anytime I hit a remainder of 1, I can really stop, right, because I know 1 divides evenly into anything. But just for completeness sake, the next step would be to do 9 is 9 times 1 plus 0. Okay, so I hit my 0 remainder. So the last non-zero remainder is 1. Okay, so the GCD of 209 and 10 is equal to 1. And then I should be able to write 1 as a linear combination of those inputs. Okay, and again, I've got relatively few equations here, so there's not too much work to do here. So now we do the extended part. So 1 is equal to 10 minus 1 times 9, and 9 is equal to 209 minus 20 times 10. Okay, so I'm going to plug this in for 9 here. So 1 is 10 minus 209 minus 20 times 10. So what is 1? So it's just going to be, okay, if I collect the coefficients on 10, I've got a 1, I've got plus 20. So it's 21 times 10 minus 209. Okay. All right, so that would be the linear combination. So my y would be 21. My x would be negative 1. We can easily see that that's correct, right? Because this is just 210. This is 209. Okay, so that means then, so 21 minus 10 is congruent to 1 mod 209. Okay, and so what's 10 inverse then? It's my y value, or 21. Okay. All right. Now, again, so this example was maybe a little bit silly, right? Because probably could have eyeballed that from the beginning, because 10 times 21 is 210, right? Which is reduces to 1 mod 209. But it's a good exercise to work through the extended Euclidean algorithm and see if we can actually use it to produce an inverse by hand. Okay. All right. So these algorithms we're going to be using all the time in all the cryptographic systems that we look at and implement. Okay. So you definitely you want to write a good implementation of both the Euclidean algorithm and the extended Euclidean algorithm for use in future homework assignments. All right, so another consequence of the extended Euclidean algorithm is what's known as Euclid's lemma. Okay, and we'll be using this quite a bit as well. And so this tells us that if we've got a number p that divides a product, and if the GCD of a and p is equal to 1, then p has to divide, so it has to divide b. Okay, so essentially what this is saying is that if p has no factors in common with that first factor, then p has to completely divide that second factor. And again, if you think in terms of prime factorizations, this should make complete sense. Because, so p divides a times b, and no prime factors of p are here, then they all have to be here. The issue with that is you actually use Euclid's lemma to prove prime factorization. So we kind of want another way to prove Euclid's lemma without having to fall back on prime factorization, which we'll do. Before we do that, let's just note that a quick consequence of this is that if p happens to be prime, and if p divides a product, well, the GCD of a and p has to be, if in the case where p is prime, it equals 1 or it equals p. So either it's p and p divides a, or it's 1, and in that case, Euclid's lemma is telling us that p divides b. Okay, so if we've got a prime dividing a product, then we know it has to divide one factor or the other, or possibly both. Okay, so Euclid's lemma is another nice application of the extended Euclidean algorithm. Okay, so to prove this, okay, so again, here we're just assuming that GCD of a and p is equal to 1. Okay. So by the extended Euclidean algorithm, we can write 1 is equal to ax plus py. Okay, so for some integers, x and y. All right, so now I want to show p divides b. All right, so in order to do that, I need to get b involved in this equation somehow. All right? And the easiest way to do that would just be to multiply both sides of the equation by b, right? Because then I'd have precisely b on the left-hand side of the equation. Okay. So let's go ahead and do that. All right, so I multiply both sides of the equation by b. All right, now I want to show p divides b. So I want to show that p divides the right-hand side of the equation. Okay, but that's immediate at this point, right? Because we know p divides ab. Okay, so p divides this term. P clearly divides this term. Okay, and if p divides both terms, then it divides their sum, which is equal to b. Okay, so p divides b. All right, so again, this is just kind of a nice quick consequence of Euclid's lemma that will be of extended Euclidean algorithm that we'll be using quite a bit. All right, and so finally, I want to introduce another important theorem that we'll be using quite a bit. And so this is what's known as the Chinese remainder theorem. And so basically, this is what's going to allow us to solve systems of congruences where the moduli involved in the congruences are pairwise relatively prime to each other. So I'm actually just going to introduce this by way of an example. Okay, so suppose we want to solve the system. And so we want to find a number x that is congruent to 3 mod 7, congruent to 1 mod 11, and to 10 mod 13. Okay, all right, so sort of a priori here, there's no reason to believe that such a number x should even exist. But why don't we just kind of try to chug through and solve it and see what happens, see if we get an answer. Okay. All right, so first thing I'm going to note here is that if x is congruent to 3 mod 7, that means I can write x in a particular form, and I'm going to write it as 7a plus 3. Okay, so if x is congruent to 3 mod 7, that means I have to be able to write it as an integer multiple of 7 plus 3. Okay, then what I'm going to do is I'm just going to take this form for x and substitute it into that second congruence. Okay, so 7a plus 3 is congruent to 1 mod 11. Okay, let me try to solve this. Okay, so 7a is congruent to negative 2 mod 11. All right, and now to solve this, I would like to just multiply by 7 inverse. Okay, I need to know what 7 inverse is mod 11, okay, or if it even exists. Well, 11's prime, okay, so any non-zero coefficient here will be invertible. And of course, we could use extended Euclidean algorithm, but that would be sort of overkill here. So I'm just going to kind of eyeball this and note that 7 times 8 is 56, which is congruent to 1 mod 11. Okay. So mod 11, 7 inverse is 8. Okay, so I can multiply both sides of this by 8. Okay, and then that means this reduces to 1 because those are inverses of each other. Okay, so A is just congruent to negative 16 mod 11, but negative 16 is also 6, I guess. Okay, so A is congruent to 6. And so then I can say, all right, well, x, I can take it to be equal to 6 times 7, plugging back in, plus 3, or 45. Okay. All right, so 45 then. And notice I just worked with the first two congruences. All right, but note 45 is a solution to those two. Right, so it is 3 more than 42, which is a multiple of 7, and it is 1 more than 44, which is a multiple of 11. So I managed to solve those two. Okay. All right, now I can hope that I'm lucky and that 45 would also be a solution to the third congruence, but 45 is congruent to 6, which is not congruent to 10, mod 13. So I need to do something else here, okay? So what I need to do here is actually note, well, 45 is a solution to those first two, but it's not the only solution. And in fact, if I were to add anything that were a multiple of both 7 and 11 to this, I wouldn't be affecting either of those first two congruences, so I would still have a solution. And 77 is a multiple of both 7 and 11. Okay, so actually, x being congruent to 45 mod 77 is the correct way to express the general solution of those top two congruences. Okay. All right, so now that I have that, I can just repeat the process that we just did. Okay. So I'm going to write x is equal to 45 plus b times 77. Plug that into the third congruence and then try to solve that. Okay, so 77 times b plus 45 is congruent to 10 mod 13. All right, and let's see, 45, as I noted, reduces to 6 mod 13, so let me do that. So let me just kind of take care of this constant term first before I worry about anything else. Okay, so 77b is congruent to 4 mod 13. Okay, now I want to deal with 77. But notice here, conveniently, 77 is 1 less than 78, which is a multiple of 13. So this is actually congruent to -1. Okay, and so here I'm using these tricks about just reducing sums and sums and products, reducing the factors and terms in those, right, without reducing the overall expression to just save myself a little bit of work. Okay, so it looks like b then is just the same as -4, which is 9. Okay, so b is congruent to 9 mod 13. Okay, so if I put all that together, then I get x is equal to 45 plus 9 times 77, and so that gives me 738. Okay. All right, so 738 is a solution to that system. Okay. But again, that's not the most general solution. So again, actually, if I take x is 738 plus anything that will be annihilated by all three of those moduli, which again would be the product of those moduli. Or let me actually write it this way. So actually, x being congruent to 738, okay, mod that product is the general solution. Okay. All right, so the point here then is that we were able to solve this system of congruences, and so let's think about what allowed us to solve it. And the key point here was that when I wrote x was equal to 7a plus 3 for that top congruence, I needed to be able to invert 7 mod 11 to be able to solve for a. Okay, and then when I got to this congruence, I needed to be able to invert 77 mod 13. Okay, which is really what I did here. It worked out to be -1, but -1 is invertible mod 13. So the key here is that the individual moduli are invertible mod the other moduli. All right, so we've got a theorem here. And suppose we've got a bunch of pairwise coprime moduli, so little m1 through mr, and we've got a system of congruences. So x is congruent to a sub I mod m sub I for each I. And then just to write down what that would look like. So x congruent to a sub I up through x congruent to a sub r mod m sub r. Okay, so I got this system of congruences. So this will actually have a solution, and that solution will be unique modulo big M, where big M is the product of all these individual moduli. Okay, so that's exactly what we found on the previous example, right? So we found the solution 738. Okay, it's not actually the unique solution. I could add any product of all three moduli and get another solution, but it is unique modulo the product of those three moduli. Okay, not only does this system of congruences have a unique solution, we can actually write out an explicit form for that unique solution. Okay, so the nice thing about this is we don't have to go through and solve that system by hand each time. We can actually write out an explicit solution, and again, so as long as we can do modular inverses, right, we can actually write a program to solve systems of congruences for us. Okay. All right, so the unique solution is given here. Okay, and so what this is then, it's in the form of a sum. So where each term is the corresponding a sub I times this big M sub I, which is basically just the product of all the moduli other than the modulus that we're sort of working on for that term, times Y sub I, where Y sub I is the inverse of the product of all those other moduli, taken mod the modulus that we're looking at. Okay. All right, so let's try to see why this works, and we're going to sort of do this. We're going to do this by focusing on what's going on with I equals 1 to start with. Okay, so the first term in our solution for x. Okay, so what is that? It's a1 times m1. Okay. Times, so big M1 times big M1 inverse taken mod little m1. Okay, what is this big M1? Okay, well, it's big M over little m1. Okay, but remember, big M was just the product of all the moduli. Okay, so big M over little m1 is the product of all the other moduli. So m2 times m3 up through m sub r. Okay. All right, so basically what this first term is doing, it's going to be guaranteeing that that first congruence is satisfied without messing with any other congruence. Okay, so the idea here is let me call this whole term z, just so I can refer back to it. Okay. So what's going on here is this big M1, right, contains the product of all the other moduli. Okay, so that's going to make this first term z divisible by every other modulus. And so that's going to mean it's just going to go to 0. Okay, so note that m sub I divides z, little m sub I, for all these other I. Okay, so z is congruent to 0 mod each of those. All right. Okay, so z is not affecting any of the other congruences past the first one. Okay, so then really all we need to know is that z is taking care of that first congruence. Okay, which it is, because what do I have? I have a1 and then I have m1 inverse, but then I'm just multiplying by m1 inverse taken mod m1. Okay, so note that z then is just going to be congruent to a1 mod little m1, because these two things cancel each other out, mod little m1. Okay. All right, so this is just kind of an ingenious trick here where we just put in one term at a time. We make sure that each term takes care of satisfying the congruence that we're looking at without affecting the other congruences at all. Okay, so that's what happens for the first congruence, but then you've got r terms, right, and each subsequent term is taking care of exactly one subsequent congruence. So the key that makes this whole thing work here is that this inverse is actually well-defined. And the reason it's well-defined is our assumption that all of the moduli are pairwise coprime. Okay, so every one of these factors in big M1 is actually invertible mod little m1, because my moduli are all pairwise coprime, and so since each of these factors are invertible, then big M1 overall will be invertible mod little m1. Okay. All right, so that will wrap things up for this class, and we will continue with some number theory odds and ends next time, and then get ready to start looking at our first cryptosystem.